I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism Podcast, an exploration of the past, present, and future of material science and engineering. My name is Taylor Sparks, and I'm joined as always by Andrew Falkowski, my co-host. And today we're continuing our mini-series with General Electric, highlighting some of the materials research happening there. Now, today's topic is on thermal spray. And I think it would be really great if you checked out our prior episode on thermal barrier coatings. That's number 48 before we get into this, because it'll synergize well with the stuff we're going to talk about today. So to learn more about thermal spray, we have none other than the gurus at General Electric. We're joined by Jim Rood and Andrea Vozar. Welcome to the show. How are you guys?
Good. Thanks for having us.
Tell us maybe a bit about yourselves, and then we can dive into this process and how it works and what GE is doing with it.
Great. So I've been at GE for 6 years. I'm a lead scientist working on performance coating, and I'm focused on thermal spray process and material development. I'm from Michigan, and my schooling is all in Illinois. So Bradley University and University of Illinois at Urbana-Champaign.
Terrific. How about you, Jim?
Yeah, I've been at GE Research for 31 years. It's been my only job since grad school, but it's been a number of different jobs just because of the variety of businesses, gas turbine and aviation businesses has really sustained my career.
Okay. Andrea, you two, has it been coatings the whole time at GE?
Mostly. So either thin films or coatings.
Okay, fantastic. Give us a very basic primer of what is thermal spray, how does it work, what do we use it for?
When I introduce thermal spray to people, I like to call it a robotic flamethrower. So it's literally, you have high power torch that you're accelerating gases through, you inject material into it and shoot it literally at a substrate. And so our fond name for it is robotic flamethrower.
This is so cool. So picture like spray paint, but instead of just your regular propellant launching the paint pigments, you've got actual flame, right?
Oh, yeah. So it has a bunch of different energy sources. So it can either be plasma, it can be a combustion gas, or it can actually be from pressure. So there's a number of different types of thermal spray, and each of those environments will interact with material differently.
Okay. Why would we use thermal spray as opposed to any of the other, whether it's electrodeposition or heaven knows there's a lot of different ways to put down thin films on things. Why thermal spray?
Yeah, it's really versatile in one sense. So it can deal with thin films, hundreds of microns, up to thick millimeter kind of deposits. It can do small parts like our aircraft engine airfoils, which are like the size of a deck of cards, but it can do large nozzles like in power turbines where they can be as big as a microwave oven. And because you have the robotics, you can do very complex geometries with high fidelity of coating thickness everywhere.
And how does the process change as you scale up to those different sizes, or does it stay relatively the same?
That's the beauty, right? It stays the same. You really just have this stream of molten material that is going to impact onto your substrates. And the deposition unit is millimeters, let's say by millimeter, and you're painting that on your parts. So other than geometry constraints, as you go big or small, it's pretty much similar.
Yeah, that isn't the case with a lot of technologies. Usually there's some trade-offs on scale, but that is really impressive. And you mentioned a robotic flamethrower. So my understanding is that this is robotically controlled in terms of the positioning of the spray.
That's correct. So we use a 5-axis robot arm coupled with a 3-axis turntable. So the degrees of freedom in motion to angle the torch specifically at the part is pretty great. And so that means we can spray parts anywhere from an inch all the way up to a meter.
So tell me about the rate of this thing. How's it compare in terms of speed of deposition to other techniques, whether those are electrochemical based or those are plasma deposition or whatever else?
It's high rate. We measure the material feed rate in pounds of material per hour, and a pass of material, because you coat this up pass by pass. We're still in metric units here, but or non-metric units here. We think about thousands of an inch per pass. It can be very thick passes and build up very thick coatings on the one end. Yep.
Sort of a naive question then. Is there a low temperature version of this? Thermal spray in its name is a high temperature process. What would be the analog? Would there be a low temperature analog to this technique? Is that just powder coating at that point?
So when we do something similar at room temperature, we literally call it room temperature spray because we do so much thermal spray, but the velocities are so different. So one of the things is that all of the thermals have a converging, diverging nozzle. That's really what accelerates the particles. And so you have a hot gas, you're accelerating particles through this converging, diverging nozzle. And although some sprays are subsonic, most thermal spray is supersonic. And so that momentum that you're getting is really what makes thermal spray. There's different temperatures. I talked about the different gases that we use. So you'll have plasma as the hottest, then combustion gases, and then the more pressure-driven cold spray or kinetics.
So what exactly is the momentum actually doing? Is it when it impacts the surface where you're getting the unique properties coming from the speed, or is it the way it's breaking the particle up as it's flying, or what is the role of the speed and the momentum?
So specifically in cold spray, I would say that's where it's the most important. And so there, metal is deposited not because we've melted the metal and allowed it to splat and redeposit on something, but we've just deformed the metal. And so in that case, it's purely the speed of impact of one metal onto another metal that is producing very rapid shear rate deformation of the metal into the substrate and giving a metallurgical bond without melting. So that's the one extreme in this case where velocity is most important. And the other extreme, perhaps, when we make thermal barrier coatings out of ceramics, yttria zirconia, which have melting points like 2700 C, there you're really relying on making a molten droplet of the ceramic that now has enough momentum that droplet is going to impact and re-solidify. But you can't just with velocity alone necessarily get a thermal barrier coating from the ceramic.
I see.
Except in some very special conditions.
So what are the sort of parameters that you have to play with when you're starting to use this technique? I imagine there's flow rates.
So there's 3 different precursors that we'll inject into the spray. So one of them is dry powder, and then another is we'll put powders into a suspension for suspension thermal spray. And then the last is what's called solution precursor. So you actually put liquids in, and then within the flame, you get a reaction in particle formation.
Okay. When would you use these different techniques?
So some of it has to do with the microstructure. So the microstructural control is going to be dependent on what type of particle size you're using. So if we talk thermal barrier coatings, you want to get it really hot, and you want these splats. And that is the technical term, it's splat. And so how hot it is and that velocity is going to form this lamellar structure that builds up on top of itself. So you get splat on top of splat on top of splat. Those form cracked, strain-controlled structures, which are great when you're doing thermal flame. Whereas, let's say you go to the solution suspensions or suspension plasma spray, then what you now have is you have to be able to suspend it into a solvent. So normally you go down in particle size to get it to suspend. Now you get more things like thickness control. And then for the solution precursor spray, that enables other materials to be deposited, right? Because you're forming it in the flame. And so sometimes less stable materials, less stable phases can get formed there. Smaller particles are other reasons people would use that one.
What does the sensitivity to some of these parameters look like? How big is the range of properties that you can get as a function of tuning some of them?
Yeah, it's pretty remarkable. Thermal barrier coating is a pretty good example. Thermal conductivity is the first thing that you want out of a thermal resistance. So thermal barrier coating is a ceramic material we put on our superalloy engine parts so that we can run them at a hotter temperature and protect the metal by having this thermal gradient through that ceramic coating. So you want a very low thermal conductivity, like your house insulation, let's say. And so yttria zirconia is already a fairly low thermal conductivity material, like 2 watts per meter Kelvin. But by changing the microstructure, as Andrea was talking about, you can get something that's down to a quarter of that, all the way up to something that's fairly close to dense. So you can really tune that thermal conductivity to be a fraction of its material property at the expense of putting in some mechanical defects into the structure. Because what you're really doing there is putting in porosity and lack of bonding to get to the low thermal conductivity.
Yeah, having that flexibility is always maybe more enjoyable, but it certainly opens up a lot, maybe opportunities and maybe some missed opportunities. How well do you think that system and all these combinations of parameters have been explored? Maybe at GE or maybe just in the literature in general?
Yeah, so the space is very broad, as you're talking about. So we've talked about we talked about the input material. Then when you have your torch, you're setting your flame that has its flame velocity by its input parameters, which are its gases and the gas flows, which give you the individual particle temperatures and velocities that then deposit on your substrate. And the substrate has its own set of parameters like its temperature and roughness. And it is a big sort of multi-variable complex space. In the years of thermal barrier coatings, which have been really a workhorse of thermal spray since the 80s and then had gone up in terms of their maturity to be used on true coating airfoils in the 90s and beyond, there's been a lot of exploration. But some of the newer material systems, I would argue you really do have a very vast process space.
And I think an example of that is within TBC. So we can do dense vertically cracked, porous, and then columnar, all using thermal spray and the YFC. So with the same material and thermal spray processes, that's the microstructural range it covers.
Yeah.
I'm curious, what's the timeline? What did it look like? Was it intentional? Did you know what sort of microstructures would evolve? Or was it just like we tried a bunch of things and we noticed that this is what the output was? Tell us about that, because these are hard things to model. So I can't imagine that they were modeled. I'm guessing this was empirical observation.
Some of the drivers for going from porous coating to this, what we call this dense vertically cracked coating. So the idea that was driven by some work here in the 80s to think about how can you get like really good intimate bonding of these splats. So like from a first principle physics idea that we have the molten droplet of ceramic hitting the substrate. What you really like to do is to get that to resolidify as like one monolithic ceramic, let's say. And so how do you do that? And so the thought was we need heat. And so let's get the substrate as hot as possible. Let's get the particles as hot as possible. And there were some observations that you could actually get these splats to resolidify and grow, almost as if they were directionally solidified and get really intimate bonding. And the consequence of that was you took out a lot of these weaknesses, and now in order to have some strain compliance, these cracks popped in. So I think pushing the process to an end where you thought you'd have goodness was the science, but then this vertical crack structure, I think, is something that came out of that work.
Jim, I think the work that you and Larry Rosenzweig and Scott Smith did in like the 2010s on the suspension spray is a good example of how just being playful in a space can come up with new microstructures.
Yeah, no, that's a good point. That's an example of we were surprised in some sense. Andrew, to your point, are there some tapped areas in the space? This is a good example of them. Yeah, thanks, Andrea. And this was when we started looking at suspension spray. All right, and so thermal spray, you have tens of microns of powders that get turned into these splats, as Andrea described them. We were looking at some literature that was saying, let's go to finer powders. So now they're micron, submicron size. Now you have to have some liquid to carry them in. And we were exploring the space. We had some insights that we might make better and denser cracked structures, more vertical cracks. And so we were pushing that space. But by doing a design of experiments, opening up this space on some of the key variables like this distance between your torch and your workpiece, the folks in Spray Cell were able to spray in a regime where instead of getting these vertical cracks, all of a sudden at a certain size of particle and a certain distance from the substrate, all of a sudden you saw a totally different looking microstructure. And it looked like these columns and these that we had seen in the evaporative physical vapor deposition process for thermal barrier coatings. Bigger, but it just popped in something entirely different.
That's so cool. Can you say something about like the homogeneity of the films? Is it very different at the substrate because of maybe substrate film interactions, and does it change? Does it go up? Can you talk about that? How uniform is it? Do you functionally grade materials intentionally, changing process parameters on the fly so you get different changes through the thick? How much exploration is happening there?
So for the more traditional processes, they're pretty homogeneous. They are set, and within the process control, it's able to stabilize. And we set it up so that it starts stable. So at a stable temperature, the flow rates of the powders themselves are stable. So that provides a uniform microstructure throughout as you grow. Now, some processes, you're building up these kind of insulating layers, and that changes the temperature properties, right? So as you build up layers. So we have seen instances where the microstructure will change as you build up thickness. Those tend not to be the processes we choose for production because they're less stable.
Okay.
Now, you did just hit on the next area of research on these functionally graded coatings. That can we use the properties of thermal spray to make coatings that change at different thicknesses, mix materials together? And I think that's going to be the next things that we can do, right? We've seen them a lot out of the MEMS world, out of clean rooms. You'll see these layered coatings, and there's no reason that thermal spray can't make that type of coating.
Okay. So thinking about future generations, right, as we move from a grant that we have right now is trying to replace nickel. We pushed poor nickel as far as I think we can push it. Maybe I'm wrong, but as we look towards future super alloys going even higher temperatures or other benefits, creep resistance, all these things, we're going to have to change the thermal spray to go with those. We're not going to use those unprotected almost for sure. We're certainly going to coat them with something, and maybe we're going to be looking at CMC, ceramic matrix composites, which we have another episode with GE. You can learn more about those. What are your perspectives on new alloys or even new CMCs going forward as it relates to thermal spray?
I think, Andrea, your work in environmental barrier coating is a really good example of this. How we've talked about the thermal barrier coating that we've done for nickel-based superalloys, but I think you found an entirely different role thermal spray needs to play in the environmental barrier coating for CMCs.
Yeah, that's true. So the needs of the substrate are really important as we do coating development, so beyond thermal spray, but just coating design in general. And so for the TBC, it's a thermal protection. And as we've used those at hotter and hotter temperatures, the CMAS, so the calcium, magnesium, aluminum sulfates, come into play, which is really just dust, right? Airborne dust that deposits on coatings. So now we're looking at a CMC, which is a ceramic matrix composite, and it turns out that it doesn't really like water, but most of our environment is made of water, and we're putting it in a jet engine, which makes steam. So we have this great lightweight, strong material that has an Achilles heel of water. And so what do we do about that? And so that's really where the EBC development has come in. And thermal spray has played a big role in the development of those EBC. But to do that, we actually had to unlearn what we did with TBCs because how the compliance works with each of those is really different. So the CTE of the metal versus the CTE of the CMC, in addition to having this new functional requirement, which is as a steam and as an oxygen barrier to protect the CMC.
So all the conversation we just had about cracks and lamella and columns to get strain compliance and good thermal conductivity, none of that is available to you if you're trying to make something that's a barrier.
And yet you still have some of the same challenges, I imagine. E-mismatch is going to cause strain, it's going to cause cracking. And so if this thing has to be hermetic, but it's going to crack anyways, then I guess much more attention has to be paid to matching materials properties up front so that you don't get this cracking. And then what do you do with thermal, right, properties? Because you still want these things to be resistive. So are these layered? Can you talk about, are you sacrificing thermal performance then for the benefit of, anti-corrosion or, I guess there's CMAS wetting and things to consider, but is it a trade-off or can you get the best of both worlds?
So as you put it, it's a design. It's a CTE match design, finding the right materials that have good matches and then building layer stacks that kind of balance CTE. That's a big part of it because once you crack through, it goes straight down into the CMC and it does become a corrosion problem. And so the structural integrity of those protective layers is paramount. Then you still have the TBC challenge on top, right? So it just adds another two layers of need, which is the steam and the oxygen barrier. What we start with is an oxygen barrier.
Like the TGO, the thermally grown oxide?
Yep. It's a silica. Yep. And then, unfortunately, silica also doesn't like steam. So we have an oxygen barrier, but not a steam barrier, not a wet corrosion barrier for that. And so then you need to make a steam barrier on top of that. And then any strain compliant thermal barrier needs to go on top of that, CMAS resistant.
He's getting our...
So as you can imagine, we go from a bond coat and a TBC in our nickel superalloy world to now we're starting to get a rainbow or the Neapolitan ice cream of coating layers, right? Just everything has to start doing something new. From a design point of view, just EBCs, the environmental barrier coatings to protect these CMCs, is its own challenge. And we're getting hotter, right? That's the other piece is CMCs are meant to get run at hotter temperatures. They're enabling engine efficiency through higher combustion temperatures. So now we're also hotter.
Yeah, that introduces some new concerns. So I personally do a little bit of thermodynamic modeling. And once you start adding more materials in layers in contact with one another, you start getting hotter and you start running for longer periods of time. Eventually, those kinetic processes do happen. And so how are you maybe modeling or trying to think about thermodynamic interactions as you add new layers and try to solve all of these different barrier problems?
It's a multi-pronged approach. Right? So it's modeling, it's experiments, it's thermodynamics, because they do talk at these temperatures. And honestly, as we keep flying planes, we're going to go hotter and hotter. So this is just going to become more of a challenge, because as you get hotter, things move faster, right? Or things that weren't moving within a material system start moving, which is a concern. And we use the experimental modeling and thermodynamic approaches to try and understand what the best system is. But what I will say is that we'll take the thermodynamics and we'll say, we think these are the interactions, and then we'll go and do pellets, right? So we'll press together ceramics and see what happens. We'll put them in these kind of harsh conditions. But then you have to make a coating of that. So the pellet is one piece, but we at GE, we make products that fly in the air that protect people, right? Like we need to make sure that safety is paramount. So then we take that pellet and we put it onto a part. And so that changes. So things that worked really well in pellets, now we have microstructure that's different. And that microstructure interacts. So we do a lot on the initial on those thermodynamic modeling. Then we go to experimentation, do down select, and then finally those interact with the engine in the engine environment. The engine environment is unique, and to get those heat fluxes in the lab is challenging. So at engine testing, we often discover new modes of failure that we then model the engine to go back and redesign the coating.
This is such a hard process, not only because you have so many layers, but you have so many competing properties you have to work with, and the service environments are so aggressive. How do you do this how do you iterate and prototype new candidate structures or microstructures, combinations in the fastest way possible? I'm guessing speed is still like a really big problem, because this is such a hard thing to solve. It's got to be many years before you get something rolled out. Can you talk about how GE is trying to do this as quickly as possible?
So we can talk about how we were doing it, which is a lot of design of experiments. So probing the process parameter space to understand what microstructures we get where, but in addition, how stable is a certain set of process parameters, right? So if it changes a little bit one way or the other, are we still going to get the same microstructure, right? Those are the two pieces as we're designing processes that are important. And the design of experiments to probe the space more broadly, and then narrowing in and finding a stable process space. However, the future needs to go faster, and the tools within machine learning are really well aligned with thermal spray, because what we're trying to do is we have a very wide multi-dimensional process space in which we use that to create a microstructure, but ultimately what we want to understand is properties. And so the future of a lot of GE's materials and coatings and thermal spray programs, we believe, is going to utilize machine learning all the way through to connect us from process parameters all the way through to performance.
Yeah.
And so we're starting with the process, but with an ultimate vision, maybe even the material, which I know is what Taylor, you and Andrew both have really put a lot of thought into.
I'm curious, what's the timeline for data collection? Is this something where you could make, after you get whatever investments you need to do for the equipment, but is this something you could do thousands of data points a week? Could you do, like, how quickly could you scale up the generation of data for this?
So in a current program, I would say it's 50 data points per week is what's planned. So not a lot comparatively.
Yeah, and for people who haven't done this, don't think that's like slouching. If I could get my students to turn out 50 samples a week, I'd be delighted. And those are much simpler things than what you guys are doing. These are hard problems. What do you do about finding it's all about, I think going forward, some of the big challenges you're going to face is that you have to have materials compatibility, but that sort of assumes that you know the materials properties ahead of time, and we don't, because especially if it's new materials or new ways of manufacturing them, you have projections about what their properties are. How do you solve this sort of inverse problem of that you need to know those ahead of time to figure out the combinations, short of just trying everything, which is not a great way to go?
So we do a lot of down select. Honestly, we'll put things into phases, and it's about taking science and turning it to engineering, is how I'll put it. Sometimes we know microstructural properties or microstructures that will move us in the direction of the properties we want, right? So, for example, strain compliance. We know dense vertically cracked creates strain compliance. We know columnar coating creates strain compliance. So we'll move down from visual inspections into that, because to get the material properties of every single iteration we've generated would take lifetimes. I know how many coatings Jim has made, and if I'm making 50 a week for a focused design of experiments, but still, to get those, to truly characterize them,
it's huge,
right? That's days to a week of time for each coating. So what we do is we use our judgment and our expertise to down select, and then we test a smaller subset, and then we get the properties for that.
Do you use lower fidelity proxies for property measurements that are just way easier? For example, maybe you don't measure thermal conductivity because it's a bear, but you just put these things under a thermal camera and just look at the raw temperature, things like that, so you don't have to do the painstakingly slow measurement?
Yeah, that we can do. I mean, part of this is doing subscale rig testing. And we have a test, it's called a JETS test. It has these propane burners, about 8 on a carousel with these 1-inch buttons. And you can screen up several coupons through that. And if you know the thicknesses and then you measure the temperatures, you can make an inference about what the thermal conductivity is in the low fidelity way, as well as then some early indications of thermal shock resistance. And so when we have those kinds of tools, we use them, yeah.
And how do you get safety factors, right? If these go on an airplane and we need that for safety sakes, it can't just a couple failed. It's really critical that you know exactly what your failure rates are. How do you assess those?
Yeah, so now you're asking the other end of the spectrum, right? The first thing was high throughput screening. How do you know when you're close? But the flight worthiness of materials at the higher material manufacturing readiness levels and technical readiness levels is a prescribed procedure. As the material moves from one readiness level to the next, the work that we do at the research center starts to taper off, and the work that's done with our colleagues at GE Aerospace or GE Power, that sort of takes off. And there are multiples of samples that produce design curves. There are, in manufacturing like conditions, with multiple sets so that you understand manufacturing variability. In aerospace engine testing is an important part of this, is that the materials need to see the environment of an engine multiple times to understand and mitigate the risk that the engine would teach you something different than your lab scale systems.
Are the people who do that different than you guys? Are you guys on the initial prototyping end and people come in later on with actual manufacturing, or is it all integrated?
It's integrated, but the center of gravity of where the effort goes shifts from the research center to the business. So stay in the loop, but the best transitions are the ones where the airspace take it on and just run with it. And it's in a state, and we've worked collectively, even in the early stages, so that that transition is very smooth. We've seen that on a number of coding systems that are flying.
And about how long does that process take, right? If you find a material and you've down selected and think that it's good, what is the timeline, or maybe even just a rough timeline to that actually making it into an engine look?
Yeah, from inception of something new to in commercial service, it's they call it 5 to 10 years. There are these in the processes we do up to this point. As you move from one technical readiness to the next, that's pretty much the pace. Hopefully, with adding some more quickness on the upfront side with machine learning type and rapid screening and engine simulative testing, that we're looking for at the Research Center for compression, because we really want to be able to introduce materials faster, but with the same level of quality that we have been, so that our engines can just perform better and be cleaner and more efficient.
So we've really been going down the rabbit hole on thermal spray for jet engines. Are there other applications that people aren't aware of where thermal spray is really important? Who else is working in this space that is innovating and changing things?
So the other biggest user, I would say, is automotive for thermal spray.
Oil and gas industry, where you have corrosive and erosive kinds of fluids, thermal spray is really good at larger inside of pipes, inner diameters of pipes, putting down hard coatings. Chrome replace when that was a corrosion coating, and that thermal spray is one of the ways that you can get away from hexachrome plating by putting down coatings. And on aircraft like landing struts was at least one of the places that was being developed for. Yeah. And I know thermal spray was at active area research. What I don't know is how well it's transitioned in other industries.
The other thing that thermal spray has been being looked at a lot for is in nuclear cladding.
Yeah, that makes sense. We've done a whole episode. We touched briefly on cladding on a previous episode when we talked about fuel particles, so I could see the application there. Corrosion is a big deal.
Have you ever revisited maybe a composition or a material that you previously had down selected away from in the past? And maybe are there opportunities as you understand the role of various dope and process parameters on the final microstructure and property?
I can say the answer is yes, because as we learn more, especially as I was talking about the coating maturation and development cycle, we talked about engine tests, right? And these are on the ground engine tests, right? Not on wing. These are on the ground engine tests. Those are the ones where we learn the most. And it's one of the reasons that it's really the gatekeeper of getting on wing. There, we've learned a lot and have had moments where we've had to go back and reevaluate. And instead of total redesign, we've gone back and tried smaller changes so that we're still within the same system, again, so we can build off those learnings and get it to market quicker.
Yeah, or maybe in testing or some of the initial tests, you found a really promising material. You don't have to necessarily say what it is, but I imagine there must be situations where you find things that just have really great properties, but when it comes to actually turning it into the application, it just doesn't spray well, or it doesn't form the right microstructure. Are there examples of that?
I feel like that happens all the time. Like, we have these technology readiness, and I've got a lot of stuff that's like right in the middle. It's never going to go anywhere. And we got a lot of great learnings from it. We learned about a material better. We learned about a process better, but it's not in its current form going to get on an engine, nor an engine test. Like I said, an engine test is the gatekeeper to the next step of technology readiness. Yeah, lots of things that look promising sometimes that kind of peter out.
Can I ask about the information and that learning? Does it end up in the field so others don't have to reproduce that same sort of null hypothesis experiment? GE is a really good company, right? You guys actually publish a lot, which a lot of companies keep their cards to their chest and they just are like, competitive advantage means keeping the doors closed. And we've been really impressed that GE has been as open as they have been. But how much of a trade-off do you have to have between trade secrets as opposed to patents versus publishing material in the open? Are you given a lot of freedom to actually publish?
Yeah, I mean, we certainly like to publish when we can strategically, right? And so when you can talk about it, certainly in area coatings where the rising tide will float all boats, you can get something out there that will help the supply chain increase, to spur some research, university research that can help flesh out the understanding of material systems, to sort of engage partners. Because one of the things we do on early TRL is do government-sponsored research. And that really is when we tie in with national labs and universities and small businesses and form these teams that can move coatings technology along faster than it could otherwise. And yeah, when that's all good reasons to publish and to get information out there.
I've just got maybe one last question. In the field of thermal spray, we've seen some cool innovations over time. You've described many different modalities, all these different things we can use it for. Is there something that you're excited about going forward?
I'm still interested in the area of suspension spray. That, as we talked about having this, you talked about all the different process knobs that you can have in thermal spray. And the idea, if we just take this one thing, which is the size of the particle, and put that into our range of thermal spray equipment and processes, and we've seen some very surprising results. The thermal barrier coating be one example, but there seems to be more that can be mined from that. And it's still just remarkable that you can really modify microstructure by looking at this one variable. It also helps us out with this issue of, we don't have to find new materials necessarily that have maybe some of these constraints around compatibility and otherwise, as long as we still have these microstructure tuning knobs like particle size to get to enhance performance and even new functions.
Is there anything that you're excited about, Andrea?
I'm really excited about bringing together what is really started as a slower development price, right? These DOEs are expensive, like thermal spray booths to run. You have an operator, there's equipment. So every experiment, every run we do in those from a developmental point of view is expensive. So to reduce the cost of that and be able to get these learnings faster is what I'm really interested in. And one of the ways I see that is when I first started working in thermal spray, actually Jim was the project leader, and we played a game with one of the microstructures. We had a microstructure, we had a bunch of process conditions, we changed them, and the question was, are they the same or different? So we literally printed out all of the microstructures that we had done with kind of replicates from different locations, put them in a conference table, and brought people in to play this game called Same or Different, which was, can you match up the 3 different pictures from each set of process conditions and say if they're, like, can you make that match together? And now machine learning can play that game with us. And so what I'm really excited is to be able to take that game and bring it into what I'm doing every day. And so we can get those learnings faster. And what I believe is that as we make those connections between the process, the microstructure, the properties, what we'll be able to do is get a better mechanistic understanding of both the process and how we connect that into designing new coatings.